do you find that the kind of ideas that you present are easily understood in an environment like the Bohr Institute?
Well, I haven't tried the Bohr Institute. I just came, but I think that scientists find it harder in some ways than many other people, you see, and some other people, because there's still a strong commitment, even perhaps partly unconscious, to the old atomistic worldview.
So what you're saying is that science has shown us something that scientists do not want to see.
Well, they have become so used to the way of seeing it that they don't want to change it. You see, they feel uncomfortable about changing it, and they feel there's no reason to change it. Many of them, they say, well, we're doing so well now, why should we change it? In one sense, it looks as if we're doing very well, you see, but if you look at the broader view, it looks very dangerous.
Now, many people are talking about this new worldview that's coming up these years. Do you see a new worldview coming up in the Western world?
Well, in a certain part of the Western world, yes. I think a worldview in which there's more focus on wholeness, on process, rather than on analysis into parts and more static constituents.
But does that come up because we want it or because we are forced to take on it?
Well, probably both. I mean, that is, I think a certain fraction of the people want it. Perhaps they're tired of the old one. They don't feel it's working. And also there's some evidence for it, I think, especially in physics and probably in other sciences as well. The evidence in physics comes partly from relativity and partly from quantum theory, or perhaps more from quantum theory than relativity.
And what kind of evidence is that?
Well, in relativity, we have a notion of a universal field, which is dynamic, flowing, and according to Einstein, particles should eventually emerge out of this as singularities or very strong regions of stable pulses of field, which gradually merge. The fields gradually merge with other particles. So we have an unbroken universe, which is in constant flow dynamically, and even the very notions of space and time have become relative, so which were previously absolute. And they may even go on to singularities like the black hole or the supposed beginning of the universe, where the present laws would break down altogether, all concepts that we know. So that's a very revolutionary view compared with what we had, say, a century ago. And then there's quantum theory, which perhaps is more revolutionary. And it's hard to explain that in a short time, but there are three main features, I'd say. One is the notion that a quantum process is in some sense indivisible, that it is one whole which it can be broken, but then it becomes an entirely different process. So each process is a whole. Otherwise, it can't be what it is. And all the quantum processes of movement are linked, as it were, into one whole. Now, the second point is the wave-particle duality, the discovery that, say, electrons, which are normally and classically particles, can behave statistically like waves when in a more precise experiment. And light, which is classically a wave, can behave like a particle in a more precise experiment. So it seems we have these two aspects which depend on how the system is treated, context-dependent, which is quite different from the classical idea that whether it's a wave or a particle is intrinsic. Now, the third point was what's called non-locality, that we find that in certain conditions there's apparently an immediate connection of distant particles. It's rather hard to explain. We can't use it for signals, but still it seems to be there. It's connected with the experiment of Einstein, Podolsky, Rosen, and has been checked by, been tested by Bell's theorem and Haspek's experiment. It seems pretty well established, right, both theoretically and experimentally. Now, again, all of these you see combined to the notion that the universe is a kind of indivisible whole, rather than analyzed into constituent elements which interact. as separately existent.
But how much can you tell about this indivisible whole?
Well, we can tell quite a bit in the sense that all the laws of quantum mechanics are concerned with it, you see. I mean, you can tell, well, I don't know what you want to know, but I mean, all the laws, you compute the properties of all sorts of things. You know, for example, take superconductivity. You know, at high temperatures, the electrons will generally scatter off obstacles in metals, and therefore there will be a resistance. You see, well, the current flow would stop unless it's maintained by a voltage. Right? At very low temperatures in certain metals, the current flows indefinitely without scattering. Now, this is a quantum effect, you see. Now, and as far as if you analyze it, you can see that it's due to the fact that the electrons are sort of held together in some way by these non-local interactions, so that if there's an obstacle, they go around and reform rather than scatter. It's rather like a ballet dance, the people going around and reforming, whereas in a crowd, each person is following his own purpose, and they all scatter. They all get in each other's way.
So this unity also creates a kind of ordering of things.
Yes, it can create a kind of ordering of things, but at the same time it explains, you see, you can see that there are situations where we have this high degree of order and others where we don't. That it's possible within the mathematics to see that when something called a wave function can be represented as a set of product of independent factors, and all the particles behave independently. But in a more general situation, they don't. So you can explain why we have so much independence in ordinary experience, and yet why, in a more careful probing, we find order, new kinds of order. So the classical level, the Newtonian level, is explained by quantum mechanics as a limiting case, you see, of a more, so that you have a whole, but the whole determines itself to behave somewhat like independent parts in many cases. So even whether it's going to be behaving like parts is determined by the whole, right?
But what we can see is the parts rather than the
well,
whole.
we see, in physics, we see the parts because that's the way we approached them in the last few centuries. I don't know if, you see, I think our perception is influenced by our way of thinking, so that we accept this mechanical way of looking at things. But if you went back 1,000 or 2,000 years, I don't think people actually saw the parts as primary. The way we see it depends on the way we think, you see.
But is it a choice? Do we have to choose between the whole and the parts?
No, well, you see, it's a question of whether you have a holistic approach, which puts the whole as primary. See, in classical physics, the parts are the primary concept, and the whole is only an auxiliary concept, which is convenient for when you have many parts working together like a machine. But the parts are taken as the basic reality, right? And saying just subjectively, we find it convenient to think about the whole. But in quantum mechanics, I think there's something else, that the whole is objective, and the parts are the result of analysis. But we have large areas where the whole behaves to some extent like independent parts.
So you're saying it's really us that make up the parts?
Well, we actually make up everything in the sense all these theories are made up by us. But in these theories, we place the parts. We may either place the parts as fundamental or the whole as fundamental. Now, the quantum mechanics is placing the whole as fundamental. That's, I think, the most basic change it makes, right? Finally, every theory is made up by us, and we are going to see whether we can apply it coherently to reality. You see that I think we could make an infinity of different kinds of theories, and some of them would be more coherent than others. You see, for example, if somebody is said to be mentally disturbed, he has another theory which we think is incoherent, but to him it looks coherent, right? Because we can always ignore what is not working, you see. Or say we'll solve that later.
You just said that in reality we make it all up, not just the parts, but also the wholes. Could you explain?
Well, I think that's the question. What is the relationship of theory to reality, you see? Now, one view is that it reflects reality, you see. Now, I think that it corresponds to reality. I think that view is only limited, right? like a map is said to correspond to a city, but there's nothing on the map that corresponds to anything in the city. In the map, you see dots of print, and the city, which is very vaguely defined, the city is also vaguely defined. So what corresponds is certain abstractions that we abstract. Right? But the map, the real test of the map is that it guides us correctly in the city. And if it's a wrong map, we will find incoherence, right, in our action, right? Now,
but it's not that you can compare this bit of the map with this bit of the
well,
city.
only in a rough sense, but that's an abstraction. You can compare it, but it's abstract, right? Now, you see, so therefore we make it all up, but the question is how coherent is it when we try to make it work? You see, that's really the key. Some theories are more coherent than others, but it's often hard to tell because when we come to a theory as broad as a worldview, we find it very hard to detect incoherence because the worldview tends to state that things that don't fit are irrelevant, or else says we're going to get them in order later. We haven't solved that problem yet. So incoherence can easily be not noticed, right? But if people are and also people would like not to have their worldviews questioned because they have got used to them and feel comfortable with them. So therefore, it's very hard to question a worldview.